Hello, today we're taking a look at VSEPR theory, and we're going to take a look at what shapes can be formed as a result of the number of atoms or non-bonding pairs of electrons on the central atom. So once we draw our Lewis structures, we are again representing where the electrons are that are being shared, the valence electrons that are being shared or not shared around the central atom, so the central atom being the one that you drew in the middle of the molecule. And from there, using what we call VSEPR theory, we can predict what the shapes of the molecule will look like. And down the line, when we're interested in talking about the properties of molecules, of substances, such as boiling points, melting points, heats of fusion, viscosity, looking at the shapes of the molecule and the polarity of the molecules can help us better understand those properties. So that's why we're doing this. Now, VSEPR theory, VSEPR, stands for valence shell electron pair repulsion. So we refer to the outer energy level of electrons as the valence shell. So that's where the VS, valence shell electron. These electrons, we're always going to be representing them in pairs because we know that orbitals contain up to 2 electrons, and when we're talking about bonding orbitals, that's the same deal. So the bonding orbitals will notice we'll be drawing pairs of electrons. So valence shell electron pair, and then the repulsion part. So the R stands for repulsion, and that's R-E-P-U-L-S-I-O-N. And repulsion is referring to the fact that these electron pairs will repel each other. And so based on how many electron pairs there are around a central atom, we can then figure out, well, if the electrons are going to repel each other as far apart as possible, then we can use that to predict the shape. And so valence shell electron pair repulsion allows us to predict molecular shapes. All right, so first thing we're going to do is start building. We're going to fill in the table in kind of a random order, so you want to just be paying attention to the number of atoms attached to the central atom. And notice you've got a column that has that number of atoms attached to the central atom, so we'll have 2, 3, or 4. For the number of unshared pairs of electrons on the central atom, that will vary depending on how many other atoms are attached to the central atom. Then the molecular geometry and bond angles we will be writing down as well. So the maximum number of electron domains that we're going to attach to the central atom is going to be 4. And there are actually exceptions to the octet rule. We have talked about hydrogen being an exception, meaning there's fewer electrons than 8, hydrogen only taking 2 electrons. But those won't be the central atom. There are actually atoms that violate the octet rule where there's more electrons than 8 around the central atom, but we're not going to deal with those. So you just need to know that there are up to 4 electron domains. So that means how many shared and unshared electrons do we have around the central atom. Okay, so let's take a look here. First off, so this thing in the middle, the purple, is a central atom. If I add one other atom, okay, so in some cases we're going to have molecules where there's just 2 atoms, like for example the diatomic molecules, hydrogen, which is H2, oxygen, which is O2. They just have 2 atoms attached, and so this is not on our data table, but it would probably be a good idea to write down. The only shape that 2 atoms can take on is a straight line. Okay, so that would be the linear shape, as well as the next example we're going to look at. So if you have only 2 atoms in the molecule, so it's not really a central atom, it's that atom and one other, the shape is going to be linear, because we all know from geometry that 2 points can only make a straight line. So there you go. Now if I add on a second atom, so this is the number of atoms attached to the central atom is 2. See, this is 1, this is 2, so 2 atoms attached. Notice there are 0 unshared pairs on the central atom. So this is the first scenario. 2 atoms attached, 0 unshared or non-bonding pairs. And so notice that the bond angles are 180 degrees. So those are the bond angles between the 2 atoms attached. The reason for this is, again, valence shell electron pair repulsion tells us that these posts here are representing pairs of electrons. They are repelling each other as far apart as they can. So the farthest they can get apart, if there's 2 of them, is 180 degrees. And so the molecular geometry, we refer to that as linear. So make sure you write that down. So the bond angle is 180 degrees. Molecular geometry is linear, and that is for 2 atoms attached and 0 unshared pairs of electrons. Okay, so we're going to add, actually let's take a look at the difference between a single bond and double bond. So let's say that I still just have 2 atoms attached, but one of those is double bonded. Notice that I get exactly the same shape. So the question about does a double or triple bond, what effect does it have on the geometry? It doesn't have an effect. So if you've got a double bond or triple bond, it doesn't really matter. You're looking at your Lewis structure. All that you're doing is counting the number of atoms attached to the central atom. So if it's 2, then that's going to be the linear shape, 180 degrees, if there's 0 non-bonding pairs as well. All right, so let's get rid of that. We're going to jump down to adding 3 atoms to the central atom. And so let's see what happens. Again, these atoms want to get as far from each other as possible. So notice what they've done is they've formed 120-degree bond angles, because if I have 3 atoms, the furthest they can repel from each other is to put themselves in the same plane and 120 degrees apart. So notice, so this is for 3 atoms attached and 0 lone pairs or 0 unshared pairs of electrons. We have the trigonal planar or trigonal planar molecular geometry. So notice the name planar means all the atoms are in the same plane. So the central atom is in the same plane as the 3 attached atoms. And notice as I manipulate this thing around, if I try to push these atoms close to each other, notice they always spring back. So you can see them like pushing off of each other. They're repelling because pairs of electrons would rather not be close to each other because they're all negative. Okay. Also notice this trigonal beginning of this name here. So tri meaning 3. So that when there's 3 atoms attached, we're going to see this trigonal beginning to the name of the molecular geometry. All right, let's add 4 atoms and then we'll start looking at non-bonding pairs. So let's add 4 atoms to the central atom. And so this geometry, notice, is tetrahedral. Tetra is the prefix for the number 4. And you'll notice that the bond angles, you might have thought, well, if 120 degrees was the furthest the 3 could get apart, then why not 90 degrees for 4 atoms? But notice that these are actually 109.5 degree bond angles. And the reason for that is, notice these atoms are now not all in the same plane. So we've kind of have this central atom here. There's like 3 little legs. And if you were to connect this all up, they say it looks like a tetrahedron, which is where they get the name tetrahedral. So notice we kind of have this little nub sticking out the top, and then we've got these 3 legs that the central atom is kind of sitting on, and all these bond angles are equal and at 109.5 degrees apart. Okay, so this is 4 atoms attached, 0 unshared pairs. So let's see what happens if I were to take away one of these atoms and replace it with a non-bonding pair or a lone pair. So I'm going to take away one of these and add one of these. So notice that I have only 3 atoms attached. So when we saw 3 atoms attached with 0 unshared pairs, we had the trigonal planar shape. But now with this non-bonding pair, so we still have 3 atoms attached, but we have this non-bonding pair of electrons, which, again, valence shell electron pair repulsion. Any pairs of electrons around the central atom take up space. So this pair is still repelling the other pairs of electrons. But notice that in a real molecule, like if I could see the molecule, I wouldn't actually be able to see that non-bonding pair, that lone pair. So it takes up space, and so the non-bonding pairs take up space, but you can't actually see them. So notice the shape is affected. So these, if these were just 3 atoms attached and no non-bonding pairs, we would see them being all in the same plane. That would be the trigonal planar. Notice that I see this trigonal or trigonal first word again, but now this is trigonal pyramidal. So notice it kind of looks like a little pyramid. So instead of these 3 attached atoms being in the same plane as the central atom, they are kind of like little legs, and if you were to connect the sides here, it would look like a little pyramid. The bond angle, so I want you to be careful of this. I want you to put less than 109.5 degrees for the bond angle. So this is 3 atoms attached, 1 unshared pair of electrons, because the bond angle, this doesn't correctly represent it, but the bond angle is actually less than 109.5, because non-bonding pairs, because they're not being shared between atoms, actually take up a little bit more space than bonding pairs. So if I just show you an example of this real quick with a real molecule, let's see here, for example, this one. Notice the bond angles 107.8. So this happens to be for ammonia, which is an example of the trigonal pyramidal geometry. And so in this pair, non-bonding pair is actually repelling these bonded pairs a little bit further, and it pushes these legs a little bit closer together. And again, in real life, you wouldn't actually be able to see the non-bonding pair up there. You just see the shape that's been affected by the presence of that non-bonding pair. Okay, so going back to our table. Okay, so let's take a look at what if I have two atoms attached and that one non-bonding pair. So notice what happens here. This is what's called a bent shape. So it looks kind of like a bent elbow. You might also see it referred to as angular. So write that down too, A-N-G-U-L-A-R. So angular or bent is this shape. So this is two atoms attached to the central atom with one unshared pair, or one lone pair. There it is there. So notice that we see this, again, this is going to be a less than 120 degree bond angle. So this is for one atom attached. It's going to be less than 120 degrees for the bond angle. Because again, we can see that it looks similar to what we saw with the trigonal planar, and that these three atoms would be in the same plane, but instead of there being an atom attached here, it's a lone pair. So that's one lone pair or one unshared pair and two atoms attached. And then lastly, we need to do two atoms and two lone pairs. And so notice this, the molecular geometry, well, just like when we had four atoms attached to the central atom, it's showing this bond angle of 109.5. It's actually going to be less than 109.5 because, again, these non-bonding pairs would repel these arms closer to each other. So this also is called the bent shape. So if I've got two atoms attached to the central atom and two non-bonding pairs, this is also referred to as bent or angular. So you'll have the same shape for one or two unshared pairs on the central atom. Okay, so we already looked at number 4. We looked at ammonia to see the real molecule. Let's take a look at water so we can see that. So this has two lone pairs on it. So notice that bond angle, it's less than 109.5. It's even less than what we saw in the ammonia molecule. So again, that extra non-bonding pair is going to push those legs even closer together. We were also asked to look at SO2. So again, you can see that, and so less than 120 because this would have been trigonal planar with 3 if this were an atom instead of a non-bonding pair. So you can see that again, the bond angles are getting slightly shorter. Slightly smaller because of that non-bonding pair instead of a bonded pair. Okay, so now we're going to take a look at symmetry, and the symmetrical shapes are going to be the ones that do not have lone pairs of electrons. Okay, so the symmetrical shapes are the ones that have 0 unshared pairs of electrons. So the ones that we had that had 0 lone pairs were linear, trigonal planar, and tetrahedral. So those are the 3 shapes. If there's 0 non-bonding pairs, those are the symmetrical shapes. And so by symmetrical, I mean that there's equal distribution of all the atoms on every side of the central atom. If we have one of these atoms replaced with a lone pair, this is where we have a non-symmetrical molecule. So anytime we've got non-bonding pairs of electrons, so lone pairs, it's going to be a non-symmetrical molecule. And what we mean by that is, even though you might say, oh, well, it looks kind of, like in particular for the bent shape, it might look symmetrical on first glance, but notice that we've got there's nothing on the top of the central atom. So we've got atoms distributed, or electrons around on these sides equally distributed, but we don't have something up here because, again, we wouldn't really see this. And so anything with a lone pair or non-bonding pair on the central atom would be a non-symmetrical shape. So those 2 shapes for that would be bent or angular and trigonal pyramidal. So if a symmetrical molecule contains polar bonds, the overall molecule will be nonpolar. So again, the symmetry of the molecule will result in a nonpolar molecule. And let's see. So the reason for that is, again, if we have equal pull, so even if I have a polar bond, if I have equal pull in every direction in a symmetrical molecule, then it is going to be canceling out the overall polarity of the bond. So I'm going to pull up the other simulation just so you can see that, and we'll take a look at that. All right, so here's an example of a molecule that, notice the electronegativity of the central atom somewhere in the middle here, and then A and C, we have the same exact electronegativity. So watch what happens. So this is that dipole symbol that I showed you, and again, the direction of the arrow is pointing in the direction of the partially negative side. So notice what happens is, we know that this bond, if we show the individual bond dipoles, this bond between B and C, well, C is the more electronegative element, and so the electrons that are being shared are being pulled towards the C atom and being spending more time there, and therefore this becomes partially negative, the B becomes partially positive, and the same thing's happening with A, which has the same exact electronegativity as C. And so this yellow shows the overall molecular dipole. So because there's nothing pulling from this other side over here, the overall polarity of the molecule is that this side's partially negative, this side's partially positive. And again, depending on the electronegativities of the atoms, that could be reversed. So for example, like what we'll see in the water molecule, right? This is the more electronegative element, so in this case the electrons will be pulled towards this side. Now watch what happens if so this is the bent shape, for example. But it would be the same deal with the trigonal pyramidal, where we've got nothing to balance out on this top side of the non-bonding, or sorry, of the central atom. So watch what happens when I put these into a straight line. And so notice that once they're in a straight line, well, you see that yellow arrow went away. And although these bonds are still polar, so the B to C bond is still polar, in this case the electrons are being pulled towards B in both cases. But notice that overall, these two arrows are canceling each other out. If you had physics, this is the idea of vectors, and if they're pointing of equal magnitude in opposite directions, they're canceling each other out. So overall, this molecule is nonpolar then. And as a result of that symmetry of the molecule, then it's nonpolar. So if we look at some real molecules, for example, we've got, well, if I just have two atoms bonded, then I know that I have to look at the electronegativity difference. So clearly H and F would be a polar bond, and therefore this molecule is polar. You can see the arrow pointing in the direction of the more electronegative element, meaning the electrons are being pulled that way. If we look at, well, here's another two-atom one. So in this case, the two nitrogens are both nonpolar. Or sorry, the two nitrogens both have the same electronegativity, so their bond's going to be nonpolar. If we look at real molecules, so we've got water, again, you can see the overall dipole, electrons are being pulled towards the oxygen. There's nothing over here to balance it out. If there's another hydrogen here, this would be nonpolar. We look at an example that is trigonal planar. So this, notice they're all on the same plane. All of these bond dipoles cancel each other out, right? Because it's a symmetrical molecule. So, again, linear, trigonal planar, and tetrahedral, those are all nonpolar shapes. So there's tetrahedral. Those are all nonpolar shapes. The polar shapes then, as long as they contain polar bonds, the molecule itself will be polar, and that would be the ones that have non-bonding or lone pairs on the central atom. And so those polar shapes or non-symmetrical shapes would be bent or trigonal pyramidal.